So our next speaker is Alessandro from the Institute of Complex Systems.
Okay, so thank you, and thanks Luke first for inviting me both to participate to the program and to this very nice workshop. And I was very happy. And when I read the list of participants, it was like, that's super efficient. It's all the people I wanted to talk with, so that's great. And today I would like to tell you a bit about pulsating active systems, as we are in an active environment, which is the work I've been doing mostly in Luxembourg in the group of Etienne Fodor, also with collaborating with two very good PhD students, which are Luca Casagrande and Yue Zhang. So I had this first slide, but I think that at this stage I don't need to motivate much about that. The only thing I highlighted, I added this red box 5 minutes ago, saying when we think about active matter, for the examples we all have given, we think about self-propelled particles. Particles that have the capability to self-propel themselves, and so they break equilibrium, detail balance, and so on and so forth. But actually, this is related to motility, and motility is the typical key ingredient of active matter. And in this talk, I would like to motivate how we can make a step further from this. So remember this message. Our focus is going to be the collective dynamics in cell tissues, or mostly our inspiration for the systems for the collective dynamics I'm going to introduce you. So the main question is, what happens when you have a dense system of deformable units that exhibit a collective dynamics? This is a typical problem in biophysics. For instance, when you have cell migration, here you see, where is the stick? Okay, on the left you can see an epithelial tissue of Magdedar kidney cells that is invading the space, and in doing so is propagating, is activated by this protein, which is kinase, ERK, whose activity regulates the cell size and shape, which is a good strategy to propagate forces, stress in the tissue, and then to invade space, and in doing so, and as you could see, a propagation of a wave of kinase. But also when the system is confined, so when it's not invading any space, you can have a very, somebody could say, turbulent behavior of the cell position, but also shapes. And if you go and if you ask a biologist that measures the actually size of the cells, they will tell you that cells fluctuate in size, and that these oscillations can synchronize, giving rise to wave propagation and patterns. So the question is motility the key ingredient that we need to describe these dynamics? And if you are still skeptical about it, and you're right if you are, I mean, it's good to be skeptical anyway. I can also tell you that this is something that happens also in cardiac arrhythmias, because in your heart, you have, in your right atrium, you have a polarization wave starting and propagating through your heart. If your heart is healthy, this wave goes back and forth without any problem, without disturbances. So this is what happens in panel C in the left side, in the left panel. But when you start developing some defects in the polarization field inside your heart, which is regulating the contraction of your cells, you start entering tachycardia. And when this, and as you can see in panel D, where you see where the polarization field has developed a defect which is causing the appearance of a spiral wave rather than a plane wave which is propagating through a heart. And when these defects multiply, then you start entering ventricular fibrillation. So this is the moment your heart is not beating anymore, you need a big shock, otherwise you die. So I hope that this is a good motivation also why I think it's fascinating to study these problems. And so we need to find out a good model to model the active tissues. So when one thinks about active tissues, one thinks about a dense collection of particles, which are cells, epithelial cells, cardiac cells. They are living, so they're active. There's continuous energy injection and dissipation at the level of the cell unit. And then what people have done so far, I just cite two main ways to study these tissues. There are also others, but I think the two of the most interesting are active vertex models, which took a vertex model, put a self-propulsion on top of the cells, making it active out of equilibrium, and studying the rigidity transition and how the self-propulsion changes the behavior of the tissue from fluid to solid. Otherwise, another thing that has been studied, and it has been studied as a strategy, especially in the study of glasses, and Elson, sorry if I brutalized your work, but in synthesis, what you can do is, when you study a dense system of particles, if you allow the particles to change their shape and to oscillate, you can actually fluidize the system and make it fluid, even in a region where you would expect it to be glassy to be rested. But in both cases, as I was saying before, we were looking for patterns and waves, especially wave propagation in an ordered fashion. And so far, including self-propulsion or only deformation, you cannot see them. So how can you see them? So this is where pulsating active matter has been introduced. So at the level, so this is a model of active matter, which has been proposed first by Yuichi Togashi and then studied by Fodor and Zhang, where you can imagine a collection of particles which have the ability to change their size. And the microscopic configuration of the system is given by the positions Ri of each particle and by a phase theta I. Before going to the dynamic equations, these particles have repulsive interaction given by pairwise interaction U, and the U depends, the small u, which is the pairwise interaction, depends on the relative distance divided by the size of the particles. And the size of the particles are actually...
If you want the stick, it's in the corner.
Thanks. Yes, I want. So, and the size of the particles is governed by the phase in this way. So this is exactly the oscillating model that has been introduced by Chung and Berthier. But what we add, as following what has been done in this paper, is a synchronizing coupling, which means that two neighboring particles would like to have the same size. And if you do that, you start in a dense system of quite distributed particles. This system, the particles grow, they fill the space, but then you can have a nucleation event giving rise to a propagation of a wave. If one wants to characterize it more, you can see that this system actually exhibits 4 kinds of collective behavior, and they can be mainly characterized by a global alignment parameter R, which is given by this order parameter. So when the system is this order, you have small density, small coupling strength at the level of synchronization, and then you have incurrent oscillation. You basically see no order. But then when you increase the synchronization, the system is able to synchronize, so the phase, all the particles are in phase, and you can have synchronized oscillation at a global level. Conversely, if you increase the density too much, you would like to cycle synchronize because every particle is pulsating with a given frequency, but you cannot. Because if you are too dense, you just get stuck, and you have an energy barrier which increases, and you are unable to oscillate to overcome this. But in the middle, in between these two regimes, you have that actually developing an homogeneity is more convenient than being all at the same phase, because you can imagine that you have a collection of particles. They're all big. They want to synchronize, but for a fluctuation, for a nucleation event, one particle is able to become small, this particle here, and so these particles make space for this particle to become big again and keep oscillating, and oscillating they will become small again, and this will make room for the next particle, and this is how a wave creates. And when you simulate the system, you look at the patterns, and you see that especially in this region of the phase diagram, where you have synchronization, the epsilon parameter here, so the synchronization that enter the microscopic dynamics, and density here, you can see plane waves, circular waves, spiral waves, where you have defects emerging here and here. And if you increase a bit more the density towards the rested phase, you see a phase which you identify as defect turbulence, because you have a continuous creation and annihilation of defects. So this is what has been done by Etienne and Yue. And this is what we were targeting, actually, because this is a way in which we introduce core ingredients in the model, a natural pulsation of the particles, repulsive interaction, synchronizing interaction, and thermal noise, as usual, and we get the wave propagation as we were looking for. Then you could ask, we can ask many questions at this point. One question we answered is this robust, or is this just for the specific setup that we choose? And this is what Luca Casagrande has been studying in the last time, and for instance, for the robustness with respect to anisotropy. What happens if instead of circular particles we have ellipsoids? And when you have ellipsoids, you can do the same analysis, but on top of the aligning order parameter, you will also have a nematic order parameter, which measures how aligned is your system. And what I can tell you, then you will see something else soon, but the phase diagram for the synchronization is robust, whereas the nematic order is quite delayed at very high densities, and it depends also on the way you deform your ellipse. Because when you have a circle, you can just inflate and deflate, but with an ellipse, you have 2-3 ways to do it. I'm happy to tell you more about that, but for the moment, I can tell you that a first take-home message is that we can say that this is a new kind of active matter that we are introducing as a way to try to describe the collective dynamics of dense tissues when you have deformable units, and that waves emerge and have been found as a trade-off between the synchronization and the rest. There is a phase diagram patterns which is promising, and there is also a hydrodynamic theory which has been developed in the paper by Etienne and Dewey, which is qualitatively good, close to the disordered state. This is the phase diagram that you obtain if you look at the fixed points of the hydrodynamics in absence of noise, where here you have a disordered phase, here you have clockwise cycling, here you have an arrested phase. Okay, but then we have some questions about it. So first is, what are the universal features and key mechanisms taking place in this dynamics? The second one is that what I show you here are patterns from the hydrodynamic equation derived to obtain this phase diagram, which again show the emergence of some patterns when you look at the amplitude of the local synchronization and the phase of the synchronization, which still are not exactly what we see and not precisely what we see in numerical simulations. So why there is this difference? Is it because of the closure uncontrolled that one needs to do when performing the hydrodynamics? Is it because density fluctuations have been neglected? Can we answer this question? And to do so, the question is if we can build a minimal model to do so. And thanks to many talks before me, I don't have to motivate that we look for a lattice dynamics that is able to represent and capture the same phenomenology. So what's the idea? How can you build a lattice model of deformable particles? What does it mean to deform? Well, you can imagine that when you are inflating and deflating, as I told you, when you are all together and you grow, you are hampered by the fact that you have your neighbors, and your neighbors are by any means an energy landscape that is breaking the continuous rotational invariance on your phase. The phase that you had before governing your oscillations is now no longer, the energy landscape is now breaking the continuous rotational invariance. And someone can say, okay, but this energy landscape will have some minima. These minima can be identified by states and then promote the state of the system from a continuous description, which is the phase, to a discrete description, which are the states, which are Q. And we take 3 states because it's the minimal number of states with which you can have a cycle. You can try to make cycles with Q states like Ising, but you won't get it. And so we define the rules of our model as a model where you have a collection of particles these particles live on a hypercubic lattice, and we will take d equal to 2 generally. They have a density which is just n over v, and the particle can change state with a given transition rate and hop from one side to each other with a diffusion coefficient. So here, hopping is totally, there is no excluded volume. You can pile up as many particles as you want, and you can do that because we are representing the potential energy in another way. Here we are only using diffusion to connect to different sites. And the transition rate mimic the dynamics of what we have seen at the level of molecular dynamics. So particles will change state from blue to red to yellow according to asymmetric transition rates, which have a driving force, F, making this rotation, this oscillation much probable than this other, more probable, and synchronizing interactions, which are nothing but the usual Potts Arrhenius rates. Having said that, okay, what happens, for instance, when we have a mini-field limit in a single site without space? Well, in this case, you have master equation governing the distribution of your states, the probability distribution of your states, and you only have the transition rate. And you can build some intuition thinking that if you have only synchronization, this is just a Potts model. You will have, after the transition from a symmetric distribution where the probability distribution is flat over the three states to an asymmetric case. But then if you introduce a driving, you have a driven Potts model. It's an out of equilibrium model, and in this case, you can have limit cycles if the synchronization is strong but not too strong that you get arrested. And you can think about that introducing a complex order parameter, A, which is given by an amplitude R and a phase psi, which is describing the state of our system and is just a linear transformation of the distribution of the states. And in the symmetric case, if you look at it from a dynamical system viewpoint, you will converge to the center, to A equal to 0. If you increase synchronization, you will start rotating. And if you increase synchronization too much, or you decrease the drive F, you will converge to a fixed point. And in doing so, you can actually define an effective potential where you're moving, and which is changing the time that you spend in each of these fixed points when you simulate the dynamics at find n, and then you will always have a probability to jump out of your fixed point if when you get the right fluctuation. And so what happens when you put this on a lattice? We now include volume, and here you see a trajectory of the system on a square lattice with periodic boundary conditions, where here you have the amplitude and here you have the phase. And you see that you have this coexistence of these domains, which are the phases of minus 2 pi over 3, 0, 2 pi over 3, which are the phases of the particle themselves, which, and here, these domains corresponds to the red regions in the amplitude plot, where most of the particles are synchronized, whereas the interfaces is where you're passing from being yellow to cyan, and therefore half yellow of cyan, you're green. And most importantly, you see that here you have generation of defects, and these defects and the waves are propagating are spiral waves coming from these defects, which are rotating in time because of the driven oscillations. So again, if you wonder if we find back the 4 phases, we do. There is a disordered phase where you see no ordering in the phase plot, cycles where the phase is oscillating altogether globally, order, which is where the system reaches a steady state in the phase and it doesn't move any longer, which is when the synchronization is very high, and also waves, which appear again as a compromise. And if you want to know how this thing are how you can put this thing on a phase diagram, on a qualitative for at least phase diagram. You can see this snapshot which change with the diffusion coefficient in the vertical axis and with the synchronization strength on the right, on the horizontal axis. And you see that mainly this is where you get arrest, waves, cycles, and disorder. So we capture the phases that have been observed in molecular dynamics. We can also characterize the phase diagram more quantitatively. But then we want to have an intuition of what's going on and answer the questions that we raised at the beginning. So we did all of this because because a lattice model is a way to make a complex system more tractable. And so we want to build a fluctuating hydrodynamics, and we do it starting from the microscopic dynamics, which is just that the number of particles in the site I at time s plus 1 with state A is just given by the number before plus a variable which is plus minus 1 or 0. Thanks to the fact that we are discrete, we can compute this thing. We can build up on the path integral approach. Here is a very good reference if you need to do this from scratch. And then you can write a fluctuating hydrodynamics for the density fields of the density of the states A, which are now constrained as rho A. This doesn't look so nice, so it's better to look at it for the right fields that we're interested, which are the density field, just how many particles are on my site, and the complex field A, which is how synchronized am I on the site and to which phase. When you do that, things get a little bit better, and you obtain equations for rho A for the evolution. And you see that rho is a constant field, as we know, because nothing is being destroyed or created. But A is not, because you can have order, and then you have a source term and source fluctuation. And most importantly, with this approach, we're able to characterize the noise terms, which are also multiplicative noise terms, but you can get this equation under the only assumption of Gaussian fluctuation. But then, again, with the equation I've shown you, it's hard to make real analytical progress. Then let's try to simplify things a bit. And we can say that, first we notice that the density field is nothing but the typical fluctuating hydrodynamic equation for a diffusive density field. And if we kill the density fluctuation, this will just converge to an average noise rho naught, which is just n over v. When we plug this back into the equation and we assume that the density converges to its steady state value, we can also simplify the noise amplitudes, making them additive. And using a perturbative expansion, we again simplify both the noise appearing in the complex field evolution, and both we expand at third order, which is we keep the least nonlinearities needed for a non-trivial dynamics in the evolution of the complex field. And with this recipe, we obtain a quasi-complex Ginzburg-Landau equation. So for those who are not familiar with the complex Ginzburg-Landau equation, which is typically used to describe the evolution of reaction diffusion systems, the black terms are the complex Ginzburg-Landau equation. But in our case, we also have this red term where the bar is the complex conjugation, and we obtain this term on top. Why? Because all these terms don't break the rotational symmetry in the phase dynamics, but this does, as we expected, because this is what we wanted to do. This is how we are mimicking the effect of the external potential. And then what we finally have to describe our system is this equation. And in this equation, we can say that we have no density fluctuation. We do have phase fluctuation, which comes in this noise term here, that we simplify thanks to the fact that rho naught is actually, that we take rho naught as a constant, and we do not consider it as we're not taking into account the evolution of the density coupled to the hydrodynamic field. And most importantly, the nice thing when you do a coarse graining is that you also have the transport coefficients, which are the factors that multiply the complex field here from the microscopic parameters, which is what you need then to compare your hydrodynamics with your microscopic simulations. And one could notice also that, okay, the continuous symmetry is broken, but the discrete symmetry still holds. And a discrete symmetry of rotation of 2 pi over 3, because we never broke the symmetry, and that this is the only term which conserves this discrete symmetry. So we could have put it from scratch, but now we also have the transport coefficients. And if you want to see if this works, this is how you simulate the hydrodynamics. And now, yes, we find back the patterns which are much more in agreement with what we find in microscopic simulations on the lattice. We didn't need density fluctuation, but we did need phase fluctuations. Otherwise, you will not find this pattern. And with this last take-home message, but I think that for the time being, I can stop here. What I would just want to say is that this is a way to describe the collective dynamics of deformable tissues. With the lattice model that we introduced, we clarified the role of fluctuation. We clarified that we can represent this as an effective dynamics of a driven particle in a periodic potential. There are a lot of open questions, I would say. I'm glad to discuss with all of you. And I have to thank all my collaborators and you for your attention.
We have time for a couple questions.
So I guess there are some equivalence classes, which is for which this is represented. So you mentioned the heart, for example. Does it? What is the connection with that kind of behavior with this toy model?
Yeah. So in the heart, what you're seeing is mainly it's close to what you see. So here, imagine you have a wave propagating back and forth without heterogeneities, so without defects, most importantly. Then defects arise. And here, if you look at this case, here we have waves which are all more or less in this region. And you have one case where you have a plane wave. This would be the healthy case in your heart. And then you have this case where you have one defect. And then if you increase the density, you have a lot of defects. So here we see a clear connection that we have a transition from, which is in the number of defects and in their lifetime. And what we still don't know is how to draw a line. You see?
Can you see some emerging patterns which can signal that you are about to make a phase transition?
Which kind of emergent patterns would you think of?
I don't know. The frequency of double periods or period doubling or anything like that.
I think so. When you look at this, I think this is an infinite period bifurcation, because you have like a cycling which become always slower and slower and slower, because without noise you would just get stuck at a given fixed point. The period doubling, I don't think so.
I think we'll have to move on, but thank you very much, Alessandro, for that really nice talk.
Thank you.